Right then, so let's have a look at this. Now I know some of us have been struggling a little bit with this, so that's why I thought I'd do an extra lesson on it. So linear regression with coded data, okay? So it's this log stuff that's particularly kind of causing a bit of confusion, and about why we go in, why are we suddenly chucking in logs with some statistics. Well, I'll come to that in just a second. Now, the primary idea about why you code data is that sometimes it just makes it easier to work with. You will be told how to go and code something, but if you just look at this first example, just really quickly, and then I'll get onto the logs bit. We've got here. It looks like really scary. It tells me I've got this. It's given by this regression line here, but it's being coded, and we need to find the regression line of S on G. So all I need to do is just do this. I just think, right, well, okay, just substitute in Y. So Y is this. Like I said, it looks scary, but it's actually relatively easy. So I want them just to follow in this through. 1.24, what's X? G minus 50. So just pop that in there, and then plus the 5.44. Okay, and then just work that through, and then you'll end up with S equals something times G plus or minus something. Okay, easy as that. All right, and they look scary, but actually it's relatively easy to do. Right, let's get on to the log bit, because that's the bit that's causing the confusion. Okay, and about why we use logs. Now, first of all, if we look at this bit just here, okay, you might be asked to work with something like this. Well, what does this what do you kind of, do you recognize this sort of form of an equation? Well, let me just, I'm just going to make some numbers up, okay? So if I wrote this down, 200 multiplied by 1.01 to the power of 3, okay? Right, just forget about a y for a second, okay? What does this remind you of? Okay, and it reminds me of a compound interest question. All right, a compound interest question. Just thinking back to GCSE, compound interest, that would have been the investment, wouldn't it? That would have been the bit that you would have started with, and this is how much it's increasing by, sort of year on year, or day on day, if you prefer. That's the actual percentage increase. It'd be a 1% increase, okay? And then that bit there, that's the time scale. So how many days, how many weeks, how many months, how many years, depends how you're measuring it. Okay, so that's the initial amount. So this is like this is a growth thing. Okay, it's about how much something is growing. Now, where the logs come in, now you'll normally kind of be told to go in like use logs on this, right? And we'll look at a typical question in just a second. But it's important to get this idea here. And why do kind of logs come in here? Well, from your basic laws of logs, you should know this. Log a n equals x. So if I've got something like that, that means that a to the power of x equals n. Okay, so just sort of rearrange it. Now that's, when you start with logs, that should be the first thing that you know. Now, and if you don't know that, remember it, because it's really important. Okay. Now, there's a really handy way of getting this, even if you can't remember, because if you because I'll be honest with you, I kind of, when I haven't done one of these questions for a while, I quite often forget, and I've got to I've just got to think about it for a minute. If I wrote down log 7, okay, all right, right. So I want log 7, right. Now, if I don't write a base, when we just write log, we take that is log 10, but we don't tend to write that down. Now, there's a really handy way of remembering this. If you can't remember, if you look at your calculator, so the log of something, so i.e. log 10. So let's just write log a n, okay, equals something. So if I were told you this and I wanted to do the inverse of it, it's 10, because that's the inverse, 10 to the power of what the answer is to this. Okay, so if you forget, have a look at that, because it tells you just there. All right, so there's no excuse not to know that. All right, I can understand a little bit confused and have to think about it for a moment. Okay, now just quickly looking at this again, thinking about basic laws of logs. So you'll quite often, you need to be comfortable about thinking about this. If I take the log of both sides, sorry, I didn't really kind of come to this enough, is that the reason that we take logs with this is that it's when we've got something to the power, okay, that allows us to deal with this bit here and think about it as a linear relationship. So we need to know about, so if I take log y, log ax, right, it's all I've done. So I've just taken the log of both sides. Right, now remember my basic rules here. That then becomes a plus, doesn't it? So log a plus log x to the n. Oh, wait a minute. Here's another basic rule. When you've got that power, it then becomes this. There we go. Just like that there. Now it might be worth writing these two things here the other way around. Right? I'll come back to why on that in a second. The best thing for us to do is to actually look at a question. Okay, so let's look at something else. All right. So here we go. Right. So here's a question. Again, looks really scary. So we've got a load of data, and I've got this thing just here. Okay. And the other thing that I want you to do with this is actually try and think, as we're kind of working it through, trying to think about what the letters actually represent. That's how they get you with those extra marks. They say kind of, well, what's the A talking about? All right. So let's have a little think about what's in front of us here. Now, if I'm looking at this, I'm thinking loggy stuff here straight away. Okay. And you might be thinking to yourself, sunshine, temperature, where's that going to come into it? Well, let's have a little look. So if I haven't actually read the second bit of the question yet, but I'm looking at this and I'm thinking loggy stuff. Right, okay then. A bit because of that power thing. Remember, it's like, look, it's that compound sort of interesty sort of thing, okay? So let's have a little look. So if I take the log of t equals the log of as to the power of b. So now, as you get better at doing this, hopefully you'll just be able to do this straight away. So then it's the log of s to the power of b, but remember that then comes like that. Now I'm actually going to rearrange this. Okay, I'm going to just, all I'm going to do is I'm just going to swap these two things around. Right, it's an add there, so why not write them the other way around? And hopefully that will just kind of link in a minute about why I've actually done that. Okay, now I wasn't actually asked to do anything with that bit of the question, but if I look at the second bit of the question, we've actually plotted log s against log t, so it sort of told me to go and do that, and it's told me the gradient to use, and it's told me where it's crossed here. So working on this here, I should be able to write down so this is the explanatory variable, this is the response variable, or rather s is the explanatory variable, t is the response variable. Okay, it's made it a little bit harder because it's got like s is sort of like x, isn't it, and t is sort of like y. All right, and again, we just got to get used to using those letters. And again, it just means an extra little, just got to think about it a little bit more, right? But it's basically the same thing. So let's come back here and just write, right, so what does this tell me here? Well, it's log s got log t. So this is like, log t is like y, isn't it? So let's write, so log t equals the gradient times by this bit, but it's log s. So log s, and then plus the y-intercept, so plus 1.14. Now, look at what I wrote down before. I wrote log t equals b log s plus log a. Well, I don't think it's too tricky, because you've written it the right way around. Notice why I swapped these bits around. Because look, there's b. Hooray! Right? So b must equal 0.16. Where's a? A's just here. Right? So a must be, so we know that log a equals 1.14. So if we just, now if you remember, what was the key thing that we said? We said you need to know this. So it's going to be the x, so it's going to be 10 to the power 1.14. If I did, now remember there's two ways of doing this, okay? And if you can't remember that bit just there, I'm just going to do 10 to the power of 1.14 to get a. Okay, so 13 point, I'm just going to do one decimal place. So it does say 3 significant figures, so that's all right. But what I could have done is I could have used this over here. So I could have just done that. And I know the answer is 1.14. There you go. All right. So I'm doing exactly the same thing. So therefore, if I couldn't remember what to do there, all right. So it's just that. So therefore, right, we've got A, we've got B. Now remember, the other things that it might actually say to us, what I should do, so should we come back really and just write out this full equation. So we've got T equals 13 point A, and then we've got S to the power of 0.16. Okay. Now another question that you might be asked is, ask me about the significance of this. Remember, that's the initial value. So that's when S is 0. Now put it into the context of the question. We're talking about sunshine in temperature. So when there's 0 sunshine, the temperature would be 13.8. All right. So try and come back to this here and actually think about the context that you've got there. Now, I've added a few questions on, all right? So if you need a bit of extra practice with these, then please have a go at those just there, all right? So I hope that maybe that's a little bit of help thinking about kind of why we use logs here. Now, there is another way of working out the A and the B value, because you could have done it from here, sort of substituting in pairs of these, and you could have then sort of used simultaneous equations to kind of work that out. It's another possibility that you could have done to estimate what A and B actually are. That can be a bit messy though, so I probably wouldn't go there. All right, but sometimes it might be an obvious route to go and take. This is really how you need to think about it. Now, it's not going to ask you to work out the gradient here, because we're all going to end up with slightly different answers, aren't we? Okay, so it wouldn't do that. And again, the axes here, you know, if I was looking at this, we would all say something slightly different there. We're not all going to say 1.14. So it would normally tell me what these things actually are. All right, so there you go. Okay, hopefully that's of some use for you. Okay.
If you enjoyed that video, please like and subscribe or leave a comment down below. Thanks for watching. I've been RMS Maths, and I'll see you next time. Maths out.